this video, we are going to look at problem 1.18 from Griffiths' Introduction to Quantum Mechanics, 3rd edition. It seems to me that the point of this problem is to just develop some intuition. So that's what we're going to do. And it talks about how, roughly speaking, quantum mechanics is relevant when the de Broglie wavelength of the particle, so that's h over p, is greater than the characteristic size of the system, d. So let's just remember that right off the bat. We're going to refer to this parameter often. So d is the size, the characteristic size of the system, whatever that really is. It's just generally how big is the system, what scale. In thermal equilibrium, at temperature T, the average kinetic energy for the particle is obviously p squared over m, and that's going to be 3/2 kBt, where kb is just the Boltzmann constant. And so the typical de Broglie wavelength then is lambda equal to this thing right here, h over this square root. Okay, so we want to determine which systems will have to be treated quantum mechanically and which ones can be described classically from just a very basic rough level estimate. So for part A, let's look at some stuff dealing with solids. And actually, before we do that, I want to go ahead and take this thing right here, and let's actually say that, you know, when d is less than that thing, h over the square root of 3m kBt, that is kind of our you know, way of knowing how we're going to treat the system quantum mechanically. So you just rearrange, obviously, square both sides, you get d squared is less than h squared over 3m kBt, move the t to the other side, move the d squared over, and t is less than h, not h bar. I've been writing a lot of h bars, so it's hard to get out of that habit. H squared 3 over 3m kb d squared. So what we're saying is, again, d is that characteristic size of the system. So below this temperature T in Kelvin, if we're, you know, using our proper SI units, we must treat system with quantum mechanics. Leave it at that. Okay, now we can actually start the problem. And so we're going to start by looking at solids. And when it talks about lattice spacings, typical solid, we have 0.3 nanometers, okay, whatever. Electrons in a solid, we want to know the temperature below which unbound electrons in a solid are quantum mechanical. And then we're going to look at when should we use quantum mechanics for nuclei, specifically using silicon as an example. So let's do that, and we'll compare with this moral here in a second. But for electrons first, so let's be clear, electrons. Obviously the mass of an electron is equal to 9.11 times 10 to the minus 31 kilograms. And so we simply plug into this formula up here for T that we already used, and we find that T is less than 1.3 times 10 to the 5 Kelvin. So when T is less than that, we can use we can use classical, we can use quantum physics, or we need to use quantum physics, and so that should you know, cause us to think, oh, well, that's a very high temperature, so pretty much always we should use quantum physics to describe electrons. That's what we're saying there. And then we say, okay, let's look at silicon nuclei. So the mass is about 28.085 times the mass of the proton. So that's atomic mass times the mass of the proton, which is 1.673 times 10 to the minus 27 kilograms, as you know. And then that is equal to 4.7 times 10 to the minus 26 kilograms. So, you know, I don't love plugging in numbers, but, you know, we're doing it for the sake of this problem. But you plug in again, and you find T less than 2.45 Kelvin we need to use quantum mechanics for the silicon nuclei. So let's go back up to our moral. Our moral says the free electrons in a solid are always quantum mechanical. Yeah, that makes sense, because T less than something times 10 to the 5th that's a big number. So pretty much any temperature we need to use quantum mechanics for electrons. But the nuclei are generally not quantum mechanical. I mean, 2.45 5 Kelvin is very close, obviously, to absolute 0. And then it says liquids are very similar. The interatomic spacing is roughly the same. It's the same, order of magnitude per se. And so it's going to be the same for liquids as it is for solids. The exception, of course, is helium below 4 Kelvin. Okay, and so you can do your own research about that one if you want to learn more about that. It's going to be for gases. So for this one, we want to know for what temperatures are the atoms in an ideal gas at pressure P quantum mechanical. And so the words ideal gas there tell us, okay, we definitely got to use our ideal gas law. So instead of PV equals nRT, though, we're going to be physicists, and we're going to say PV equals capital N kBT, where N is the number of particles or molecules, Kb is our Boltzmann constant, and rather than little n for moles and R for our other constant. So let's let N equal 1. So 1 molecule. Molecule's not really a unit, but I'll just remind us what we're doing here. Let N equal 1 molecule. And let's let V, the volume that we're in, be equal to the characteristic size of the system squared, or the characteristic length, cubed, not squared, obviously, so cubed. So then what we're really saying is that PD cubed is equal to KB times T. And so thus, D is equal to rearranging KBT over P, pressure, all raised to the 1/3 power. So let's go back up to what we found earlier. We said, hey, T is less than this. Let's bring that down. T is less than that means use quantum mechanics. So I just erased the D squared there. I'm going to put it off to the side. So this then is equal to H, not H bar, again, H squared over 3m KB times 1 over D squared. Well, we just found what D is here, so let's just plug that in. And don't forget to square it, and we're going to have to flip everything because it's in the denominator. So when we do that, you get P over KBT to the, not 1/3, but it's squared, so 2/3. Perfect. Okay, and so let's just rewrite it now with T less than out front. So T is less than this. That's what we're saying. If we apply the ideal gas law, this is what we're getting for a system with a volume equal to the characteristic length cubed. Okay, T to the minus 2/3 over here means let's multiply both sides by T to the 2/3. So we have T times T to the 2/3 is less than H squared over 3m KB P over KB to the 2/3. And then, so this is T to the 3/3. 3/3 plus 2/3 is 5/3. So T to the 5/3 is less than H squared over 3m, and then P to the 2/3. And then we can do the same thing with our KB. That's KB to the 5/3. And then we just need to undo that. So we put everything to the 3/5 power. And we get that T less than H squared over 3m to the 3/5 power. And then we have P to the 2/5 over KB by itself. And then we just compare, and Griffiths says that this is, in fact, exactly what we should get. And so we are definitely good on that front. All right, so then, sorry, I'm scrolling all over the place. So then it says, put in numbers for helium at atmospheric pressure, and then we're going to do hydrogen in outer space, and then it gives you some more information. So for hydrogen in outer space, when we get to it, the interatomic spacing is going to be about 1 centimeter, temperature about 3 Kelvin, and then we're going to assume monatomic hydrogen instead of H2. So just one atom of hydrogen, not two of them, even though we know that when you find hydrogen, you're actually finding two of them. But for the sake of this problem, we'll just do it like this. So simplify the model a little bit. So helium, 1 atmosphere is equal to 10 to the 5th newtons per meter squared, and that's equal to our pressure for this problem. The mass is approximately 4 times the mass of the proton, which is about 6.8 times 10 to the minus 27 kilograms. And so then we just plug in and solve for T, and we get T less than 2.8 Kelvin. So for T less than 2.8 Kelvin, we should indeed treat helium as a quantum mechanical system. And then for hydrogen, monatomic hydrogen, we have that the characteristic size of the system, D, is approximately 0.01 meters. Let me clarify that there. Okay, there we go. Sorry, I had a thought that we were using the wrong number, so no, it's 1 centimeter, so that's 0.01 meters. And then we know that the mass is about 2 times the mass of the proton. There we go. It's 3.4 times 10 to the minus 27 kilograms. Therefore, by the same formula, T less than 3.1 times 10 to the minus 14 Kelvin is our value there. So with the temperature in outer space equal to 3 Kelvin, we can certainly make that more clear. We can certainly treat monatomic hydrogen by classical thermodynamics. So classical thermodynamics is totally okay for that sort of problem.